The Fermi Paradox. Part 19. And Still the Silence. So where, after this long journey, does this leave the Fermi Paradox? If, as looks increasingly likely, other complex life forms are fairly common in the galaxy, how does that resolve the question raised by Fermi and Hart? If the galaxy has apparently done its best to lay out the red carpet for intelligence, should we not see evidence of it everywhere? The question Fermi asks all those years ago still stands. Where is everybody? For all the evidence we've gathered, for all the knowledge we've gained, the problem with resolving the paradox remains the same. We simply don't know what we're dealing with. In Part 7, I outlined the evolutionary argument for the rarity of intelligence. But in reality, that argument, while certainly compelling, is still an educated guess based on a sample of one. Us. Citing it is similar to citing the rare Earth hypothesis. For all we know, our planet may be unusually ill-suited for life, as has been argued by several astrobiologists. Conversely, taking the more optimistic tack of Carl Sagan and Frank Drake, who argue that intelligence will form wherever it can, is just as presumptuous. Ironically, until we actually locate another intelligent civilization, we will have no way of knowing how likely intelligence is. After 4 decades, is there a way to answer Hart's challenge? One of the most obvious answers as to why we have found no evidence of extraterrestrial intelligence after nearly 60 years of searching is that they are simply too far away. Optimists for alien contact often cite sheer numbers as evidence for intelligence elsewhere. Given the number of stars in our galaxy and the number of galaxies in our universe, then the suggestion that we are alone is not only unlikely, it borders on solipsistic. There is, however, a fundamental flaw in this argument. It is sometimes said that there are more stars in the universe than there are grains of sand in all the beaches of the world. This is not in fact true, at least for the universe that we can see, though the estimates are fairly close. Even if it were, most of these beaches are closed off to us, probably for all time. If life evolved in any of the 100 billion distant galaxies that we know are out there, then it will remain lost to us, forever stranded by the speed of light. The nearest large galaxy to Earth, Andromeda, is 2 million light-years away, which means that any civilizations within its borders that our super-advanced future telescopes may be able to detect will be 2 million years old and possibly 2 million years dead by the time we see them. And forget communication. It would take longer than the lifespan of a species just to exchange hellos. And the same goes for the aliens themselves. Since many SETI programs presuppose that aliens would be interested in sending us a message, such cultures would have to be close enough to observe our development as a civilization. If they were a mere 100 light-years away, they would look toward Earth and see a culture only just moving beyond steam power. If they were 1,000 light-years away, they would see a world still depredated by Vikings. Without faster-than-light craft, which, unless we invoke magic, we must assume they cannot have, they will have no way of knowing how our culture has developed, or even if we're still alive. In short, anyone attempting contact within their lifetime should focus their hopes on the 20,000 or so stars within 50 light-years of the Sun, not only because he or she stands a chance of living long enough to achieve it, but because any civilizations in that range might just judge us as worthy of their attention as we have. This means that for us to have any real chance of contacting a civilization, the probability of its existence would have to be as high as 1 in 20,000. About as likely, in other words, as dying in a plane crash. Given how many of us fear flying, that is a demanding number. Another possible answer was put forward, naturally, by Carl Sagan. In 1981, fresh off the success of Cosmos, he published a paper that was essentially a riposte to Hart's argument. In the paper, Sagan proposed a diffusion model based on blast wave physics, soil science, and population biology. When run with Hart's assumptions intact, the model produced a very Hart-like pan-colonization timeframe of 30 million years. However, Sagan did not accept Hart's assumptions. Van Herner had previously shown that even if interstellar colonization proceeded at the speed of light, within 500 years the, quote, empire would consist of a sphere with a radius of 160 light-years, with every habitable planet within it, full to bursting with inhabitants. Therefore, Sagan argued, expansion to other planets cannot solve overpopulation, and any species wishing to survive indefinitely must eventually practice zero population growth. With the model reprogrammed with zero population growth in place for every colonized planet, the time to pan-colonization suddenly became 13 billion years, or the near exact age of our universe. Thus, the Fermi Paradox was solved. Aliens were everywhere, but the reason we saw no evidence for them is because they have been studiously applying zero population growth, and thus had not had time to reach us. If that conclusion seems rather awkward to you, you aren't alone. A number of writers on the subject of ETI have raised objections to Sagan's hypothesis, mainly that it too falls into the planets with hats trap. As discussed in Hart's episode, the planets with hats fallacy is the idea that any and all members of an alien species would think and act the exact same way. Sagan, in fact, goes much further than this. He places the hat on an entire galactic empire. It's one thing to assume that a single overcrowded planet facing resource exhaustion would practice zero population growth. But a small group of colonists on a virgin planet with millions of square miles of unclaimed land? In such circumstances, not only would population growth be expected to happen, it would be rather critical, as it ensures your colony isn't wiped out by a single bout of Vulcan flu. Sagan also assumes that the ruling planet would be able to assert its zero population growth ethos on an entire empire, but how could it maintain control over such distances, let alone over thousands or even millions of years? Sagan was not the only scientist to attempt to resolve Hart's arguments. In 1993, Jeffrey Landis of NASA's Lewis Research Center proposed an alternative model for the expansion of an extraterrestrial civilization based on the mathematical model of percolation. Yes, the same percolation that occurs in a coffee machine. This model countered Hart's argument by assuming a number of base facts. First, that interstellar travel is costly and difficult, and there exists a maximum radius beyond which it is not feasible. Second, that interstellar communication cannot exceed the speed of light, and thus would take thousands of years to cross galactic distances. Also, travel and colonization times would be on the order of centuries. No interstellar species, therefore, could maintain cultural hegemony over its galactic empire, and multiple independent cultures would soon emerge. Finally, he assumed that it is impossible for any civilization to conquer and recolonize an already established world. Landis justified this assumption on the grounds that any attempt to conquer a populated world would be vastly more difficult than colonizing an uninhabited one, and so is unlikely ever to happen. With these three assumptions in place, Landis divided his prospective interstellar cultures into two camps: those with a drive to colonize and expand, and those without. If a culture has a drive to expand, and has stars within reach, it will colonize all the stars it can. If it finds itself in a region of the galaxy with no stars within feasible reach, or in a region in which all feasible systems have already been colonized, it will lose its drive to expand and remain locked on its home planet. So what does this have to do with coffee machines? Well, when these assumptions are plugged into the mathematical models for percolation, they always, no matter what the numbers, result in arbitrarily large voids between clusters of colonized worlds. Eventually, the patterns of colonization begin to resemble fractal dragon curves. Thus, Landis concludes that the Fermi Paradox can be resolved by assuming that our system happens to be in such a void. Landis's argument is in many ways superior to Sagan's. As he points out in his paper, his assumptions are less restrictive than those imposed in Sagan's model. Nonetheless, Landis still falls victim to a variant of the planets with hats fallacy. Rather than assuming what one alien race would do, it assumes what multiple alien races would not do. In this case, conquer and invade each other. While it is arguable that invasion makes little sense when easier colonization options are available, beyond a certain point, local resources will be depleted enough to justify an attempt. Landis's argument best applies to interstellar cultures in an early, pioneering phase of their expansion. But Hart has already shown that our galaxy is old enough for every star to have been colonized 1,000 times over. Our global civilization is barely 500 years old, and yet we're already confronting the issue of diminishing resources. How long would it take for a civilization to exhaust the resources of its star system? 1,000,000 years? 10 million? 100 million? Even at these timescales, Hart's argument still holds true. But what if there was a different reason for the Fermi Paradox? A reason less to do with our stars and more with ourselves? It is a reason we will be examining in the next episode.